And that would depend on like the kind of duty cycle that you might have on that particular system and what kind of frequency. So millisecond range is often the case, not necessarily. So these aren't switches necessarily that have to move fast between state 1 and state 2, but they do need to make sure that the energy that passes through them, essentially that they're not distorting it at all, that they're not adding any loss at all. Like that would be essentially the goal for all those. So it's directing the RF energy from point A to point B. Oh, sorry. You do. So just like with amplifiers, the matching networks are very important, and that's for all of these different kinds of components. So that's going to depend on your frequency range that you're operating in, and that also has to be accounted for as well. Now those are can be, depends on the design, but a little bit more straightforward to put into it, so that it's the switch performance that's going to limit you. But that's really, it's those matching networks that kind of define what frequency that you're expecting that switch to operate within.
So the switch, the amplifier is going to take, right?
So they don't have to be, but ideally, yes. Particularly as you go to higher frequencies. As you go to higher frequencies, then when you start to try to combine, different substrates, different chips, the parasitics that are involved with combining those become very important, particularly your parasitic inductances. So ideally, this is what you want is this entire process to be on a single MMIC, and then that really, helps to eliminate a lot of those problems. As you go down in frequency, that's less of a problem. But as you go down in frequency, it's easier to get a good switch performance. So once again, it's not as important. So how I like to kind of reference this is that traditionally, I'm sure I think that's Model A on the left. That's kind of an old style amplifier, and then the right, that really rough road, that would be your traditional RF switch. And what the industry has been focused on in terms of improving it is making a better amplifier. So making really fantastic high Fmax, high FT amplifiers. The problem is that the switches are the same bad switches that people have been making for the last 30 years. And so now you have this really fantastic amplifier essentially going over a really crummy road. And so the RF switch, in this case, whether it's being used in a phase shift architecture, attenuator, et cetera, it's helping to guide the RF energy and shape it as opposed to amplify it. But those losses, of course, affect that signal. And what we want are both those worlds. We want to have a great amplifier. We also want to have a great switch to go along with it, so that we actually can see the quality of that amplifier.
Provided though you don't have speed limits.
Provided you don't have speed limits. That's right.
Which is what you're going to have. You're going to have a lot of components.
Well, you do have to be careful about the RF police, and they'll yeah. All right, so what are we looking for in an RF switch? Okay, we want to have something that gives us very low on resistance. That correlates to low loss of the switch, but also a very low off capacitance. That gives us our high isolation that we're going to expect. We want to make sure that our systems aren't talking to each other. We also, of course, really want to have power and linearity, and so that translates to a high current carrying capacity as well as a high blocking voltage. Finally, we want to make sure, ideally, we'd like to have a switch that doesn't dissipate any power of itself. That can switch very fast, so we want to have nanosecond switching. And finally, we want to be able to integrate this thing wherever, in MMICs, wherever we want, with ease, without crazy voltages. And we want a reliable device. We don't want to have something that's going to switch 10 times, 100,000 times, 1 million times and fail on us. We want this thing to have a mean time to failure in the tens of billions, so that it's an I don't care kind of a problem. Now, how those things are kind of related, these are all, in terms of the trade space, they're kind of connected to each other. And in particular, just as in power amplifiers, it's well understood, people understand that there's a power frequency trade, for example, that people talk about. If I go higher in frequency, I'm going to lose my power. So that's kind of an intrinsic nature. For switches, how I like to refer to it is that there's a loss isolation in frequency bandwidth kind of triangle, which is analogous to that. And in particular, if all I care about is a narrowband system, then I can achieve low loss and high isolation. But to get all three of those things simultaneously, that's really restricted to get a wide bandwidth, MI-loss, MI-isolation. That's really restricted by the nature of the fundamental nature of your technology. And that's because when we talk about narrow bandwidth kind of things, I can do circuit tricks, what I would call circuit tricks, because I'm not an RF designer, so I'm allowed to call them tricks, where I do things like resonate out, capacitances and things like that. And so the device still, the switch, even though it's not a great switch, still works like I want to, and I can get the performance I'm looking to. But that whole ballgame changes dramatically as soon as I say I need to have a broadband system. And so broadband system, what I mean multi-octave. And what I'll be showing you later is, for example, is 1 to 18 gigahertz. But even when I'm just looking at 2 octaves, 2 to 8 gigahertz, for example, that still applies for this kind of thing. Now, when I'm talking about switches, I'm going to spend a lot of time specifically referring to what's called a single pole double throw switch. So I'm going to spend a little time explaining what that is so everybody understands what kind of switch. And the reason is that if you go into the literature, you have to be a little bit careful when you start reading people's claims of, I got this great low loss switch, because sometimes, and I've encountered, that what people will say that they're a low loss switch, they'll really be talking about a single pole, single throw switch, many times in a shunt configuration, and I'll show you later on. You have to be a little bit careful about that, because when they say that this is really low insertion loss, are they really talking about the switch, or are they just talking about the transmission line that switch is running off of? Those kind of tricks are much harder to do with the single pole double throw switch, but I find it much better to, when you're comparing technologies and to make an apples to apples comparison, to use a topology like this as your baseline. In particular, I'm going to explain what what's called a series shunt double throw switch. So that's what the topology you see on the left is. And so in this case, I'm showing, okay, what happens when I'm trying to get in through the energy from RF in through the pole out through throw A. So my energy goes through my series switch. That's in the on state. The shunt switch is what that A shunt switch is dangling off towards ground. That's in the off state. And the B shunt switch on the lower arm, that's in the on. So A series, B shunt are simultaneously on. The B shunt series makes sure that any energy that's coming in through RF out is shunted straight to ground, so it's not interfering with my signal that I'm trying to pass from the RF in to RF out A. And then likewise, my B series device and my A shunt device, those are both off. So that means that the signal, is blocked from going through from RF in to RF out B. And likewise then, if I switch my poles and I go from my input to my throw B, now it's the same thing, but now my signal once again is isolated, and I'm just getting my signal through from RF in to RF out. Yes.
On your third, point, multi-throw switches, etc. The RF decides different paths, right?
Correct. So that's
now, what is kind of like, how can you make sure the reflected components and everything else, you don't have so much as a reflected component that nothing is going to go through? Right.
That's really where your matching comes in. So you're absolutely right. Like all the RF design comes down to, how can I trap the RF energy so it goes where I want it to go? And you have to worry about reflections as well as isolations. And I like this topology in particular because when you look at what the insertion loss is, it's very telling, because in this particular topology, things like isolation and reflection problems also show up as insertion loss. You can't hide from bad isolation and bad reflections like you can in some of the other topologies because they show up right there. In terms of what those reflections are and whether or not it's happening at those interfaces, that does come down to the actual circuit design itself and making sure that your matching network is appropriate.
Always one is on, right?
Always one is on. I mean, you could make everything off if you wanted to, but I mean, generally though, you're either going, like I don't show right now in terms of my logic diagram of how I'm biasing. I don't show what happens if I turn everything off. You can do that. There are some applications where You do in fact want to do that for at the system level, but in general, you're either going, it's signal going this way or that way. Those are the two dominant.
Like matching and isolation.
Yes. All right, so if I go and I look in the literature, and this is my own personal, what I have found, like the very best examples of broadband single pole double throw switches for a variety of different technologies, including RF MEMS, gas pin diodes, and then a bunch of different FETs, gallium arsenide PHEMS, GaN HEMS, and CMOS, usually NMOS, silicon devices, whether on SOI or bulk. And you look at what kind of single pole double throw switch performance people have published, that are broadband, and compare them, you see that there are really two different regimes in terms of performance. That for low broadband loss, you have the RF MEMS and the pin diodes, and those are less than half a dB, very respectable, with high isolation. So high isolation, and generally you want to have certainly at least 20 dB, but for most system applications you want to have 30 dB, sometimes even higher, as a minimum. But once you get, once you hit your minimum threshold of isolation, you don't care so much. For insertion loss, you want that to be as low as possible. Every tenth of a dB lower you can get is of benefit. But so as I was saying, that you have these low loss technologies that we really like. We'd like to have that kind of low loss. But then we have the FET technologies. Those are all have a significant loss. So what you can see for broadband switches, we're getting over a dB of loss. And now remember, as I said, we're talking in a system, you might have 60 of these switches. So 1 dB, okay, it might not matter, particularly if it's not on the front end. But I suddenly have 60 of these switches. That's 60 dB of gain that I have to make up into the system. And so you're talking about a lot of additional power to make up for that, and the linearity impact becomes quite significant. So, yeah, please. Yes, both of these are S21, and it's just whether or not. So it's S21 from the through the on path, and then the S21 of the off path. That's a comparison of those two.
The other way.
Right. Yeah.
Right. One loses the current.
So, but at the same time, FETs have all kinds of properties that I really like, when I'm talking about RF systems, which is to say that in general, one, they're higher reliability. I don't really have to worry about them ever dying or breaking on me. Also, generally very low power consumption. So it doesn't matter how many switches I put into my system. They're also fast. And these are things that I can't say about MEMS and the pin diodes. So RF MEMS, I worry about the reliability, certainly. With pin diodes, I worry about the power consumption. It's a great technology, but it can be hard to integrate. And as long as I only need 10 of them, I'm okay. Once I need 100 of them, 1,000 of them, they are vertical devices. And in fact, they can be. So RF MEMS, it's really kind of a goal in terms of performance, and RF MEMS is great. MEMS in general is great for all kinds of things, but RF MEMS has been very difficult to meet the promise of what it was. When I first started at Northrop Grumman, I was in the height of the MEMS days, and that's actually kind of what got me started down this path. In that my mentor at the time, what he asked was, why can't we build a FET device that works as well as an RF MEMS device? In terms of the loss performance. And so that has been kind of like the guiding light behind all this analysis and project. Of course, there is a solid-state device that works as well as MEMS, and that's the pin diodes, but there are all kinds of caveats associated with the pin diode. Number one is that power consumption. There's a number of applications couldn't tolerate that, the power consumption, where you're looking at 10 milliwatts approximately per pin diode of just DC power consumption. But on top of that, though, you also have to worry about how you're going to do the design, and that's because the pin diode is a 2-terminal device, not a 3-terminal device. That really complicates your control mechanism for that pin diode, how you insert it into the circuit. Generally, that really limits the bandwidth. In general, it's just a really hard technology then to really access and use because of that. So if I go and look at just FETs now, so why is it that I can't just get a FET that just works great? I should, right? I mean, amplifiers keep on getting better. And in fact, if I look at the figure of merit for amplifiers, both FT and FMAX. FT is unity, the theoretical frequency at which you reach unity current gain, and FMAX is the theoretical frequency at which you reach unity power gain. There has been a dramatic improvement whether you're looking at CMOS type technology or 3.5 technology. And so the plot on the left, I kind of depict as a function of time what you can find in the literature for reported FTs and FMAXs. And really what this is a demonstration is that those technologies responded really well to essentially shrinking the gate and further making all the dimensions that they're using smaller as they progress the process technology. But on the right, and I'll get into a little bit more detail about what the figure of merit of switches, but the RF figure of merit for switches is this FC0, the cutoff frequency, and that's the theoretical frequency at which the switch stops operating as a switch, the ratio of the off impedance to the on impedance. And if I do a similar kind of plot as a function of year of what people have reported for that FC0 number, you'll see that it's actually a very flat kind of response. There has been some improvements, but I can find in the very first FET RF switch papers published in the 80s, when people first started experimenting with gas MESFET switches, FC0 is around 500 gigahertz. And if I look in the literature today on the latest GaN RF switch, I'm going to find FC0 is around 500 gigahertz. And so, there's this shocking dichotomy between these two. And it's interesting because, what the focus has always been, as I said, on developing a better amplifier. But when it comes to switches, the general practice, as far as I can tell, has been take your very best amplifier and just move that gate into the center of the device, and you call it a day. And unfortunately, that doesn't really do very much for you for improving that RF switch performance.
Developing amplifier, meaning you need analog device.
Correct.
I'm saying it because I have a student over there. This is my class. I mean, as opposed to so the switches.
Right, that's right. And so here's an example. So when I'm talking about amplifier and switches, this is illustrating what exactly I mean. So on the top, I'm showing what I mean by an amplifier. So it's a very simple, common source configured amplifier, but suppose you put in an RF signal onto the gate, and then because you're going across this load, when you have a voltage supply on the drain, that's essentially translated into a higher response across that load in terms of that signal. On a switch though, now instead of putting that RF signal on the gate, I'm putting that RF signal on the drain and just passing right through the device. And what I want to do is either pass it through or not. And I'm not trying to distort it or change it. I just want to allow that signal through or not allow it through. And that's really important because what that means is that the capacitances that are going to govern that behavior are different. So with an amplifier, it's all about the CGD and CGS. So I show F sub T, but it's even more so if you look at Fmax, you look at like the Miller capacitance. That gate to drain capacitance is absolutely critical in terms of what your resulting amplifier performance is, which is why the practice is to move that gate as close to the source as possible, and you minimize the source resistance and all those things. And those kind of things, when you do that, you're going to keep on making a better and a better amplifier. But for a switch, in contrast, you're going to care about this off capacitance, which of course is is in large part this drain to source capacitance. So let's go in a little bit more detail about where that really comes from. And so something that I've developed is trying to think of this as, what is the most basic fundamental aspect to it? And so if we're just going to look at a fundamental idealized block, so now I'm ignoring, this will be true whether or not it's a FET, a MEMS, a diode, doesn't matter. I'm not presuming any particular type of device, just a arbitrary blocking material. I want to have an RF signal that goes from one end of the RF signal to the other RF signal, and either pass or not, right? That's what I'm expecting my switch to do. So how well is this arbitrary imaginary material, fundamentally, how is it going to operate? So in the on state, it's going to be a resistor, right? I'm going to characterize this block of imaginary material by its resistance. in the off state, it's going to be two things, right? It's going to still be a resistor, but now a much higher value resistor, hopefully. But it's also going to be a capacitor, where I'm going to expect some sort of capacitive coupling between my two nodes there. And so that essentially gives me my my on impedance, my off impedance. And as I said before, that for an RF switch, right, I want to have low impedance when it's on and a high impedance when it's off. And that ratio, when that ratio, between the two, that essentially tells me what my quality of my switch is, how good it is. If I want to have as big of a difference between the off state and the on state as possible. So if I take that and then I set it equal to, first actually let me go through it. This is just demonstrating that, so that impedance ratio is 1 over the frequency times 2 pi R on C off. And I will note that with this arbitrarily shaped block of imaginary material, right, I can also now think of, okay, well, what is this capacitance of some random block of material? Well, it's going to be associated with, of course, the cross-sectional area of that material and its dielectric constant in terms of the off capacitance, and then conversely, a ratio of that of its cross-sectional area and its length as a function of its conductance. But the interesting thing is those two things kind of cancel each other out on each other. And so if I go and set that impedance ratio equal to 1, and I solve my equation then of course that gives me my 1 over 2 pi R on C off, but that then essentially drives down to its conductivity of this imaginary block of material over 2 pi epsilon. And all my geometrical effects, right, they balance each other out, because if I make a bigger device, if I try to make a larger cross-sectional area, that drives down my on resistance, but it increases my capacitance area just as fast. If I make a larger separation between my input and my output, the longer that I make it, that increases my resistance while decreasing my off capacitance, once again, by the same amount. And so fundamentally, it's we're talking about a material property, not a dimensional property for RF switches, which then, kind of locks me into this initial box here. If I go and talk now related back to semiconductors, my conductivity is going to be related to my charge density and my mobility. And so fundamentally then, what that predicts is that my cutoff frequency is going to be equal to the charge density I can get in my material times the mobility divided by its permittivity.
That's kind of surprising.
Yes, that's right. So, and I think an interesting result that I'll poke at a little bit further later on. So now I'm going to go and then relate that performance to, okay, well, what does that mean from an RF standpoint? And even though that, like I just told you that, I don't like comparing, when I'm comparing technologies to use single pole double throw switches, single pole single throw switches, it is really useful just to give everybody a feel for how R on and C off relate to insertion loss and isolation, because there are well-defined equations that use what your R on C off values, as well as what your matching networks are, in order to determine what your predicted insertion loss and isolation are. So in these equations, R on C off, the Z0 is that impedance level, which generally is 50 ohms for most RF systems. And you can have a series device, a shunt device, and you can put them together and make a series shunt device. The performance that you expect that I have plotted, so the first plot right there in the center, that's a series device. The light blue is the insertion loss, the dark blue is the isolation. On the plot to the right of it, that's the shunt device. And the important thing for both those is that what you can see is that you can trade back and forth between insertion loss and isolation. So the x-axis in all these cases is the off capacitance. And for a given FC0, right, that's a fundamental nature essentially of your device, a characteristic of your device, then I can design a device that's going to be, have a higher off capacitance, which will then mean it has a lower on resistance. And that trades me where that decreases my insertion loss, but also decreases my isolation at the same time. I can do the same kind of thing with a shunt device. In a series shunt, it's kind of interesting because that's kind of like a simplified version of a single pole double throw switch in that case, once again, you have the case where isolation turns into loss, that anything that doesn't get through and starts leaking out the second device in there starts to show up as the insertion loss. And that's why you end up seeing, instead of a relative maximum, so to just use narrow, so what I want is, the biggest, when I'm doing my design, I would want to have the biggest difference between my insertion loss and my isolation. That's kind of like the optimum point, and I can kind of find where that is. And of course, at some point, they get close together, and they're not really working anymore. But with a series shunt device, right, the distance between the isolation line right here and the insertion loss right there, they're roughly parallel to each other. And I can't infinitely trade back and forth. That there is, in fact, like kind of an optimum point, a trade between what my insertion loss is, what my isolation is, because of the feedback that you get between the two different devices talking to each other. All right. So if I zoom down into the device and break up and look at from a circuit model, this is fairly conventional in that I have a bunch of different kind of resistors. I have my channel resistance. I have my two contact, my drain, my source resistance, as well as some parasitics. And when in the on state, essentially this all collapses down into RD plus RDS plus RS. And similarly, in the off state, then I'm just looking at these parallel capacitances, the CDS in parallel to the CGD plus the CGS. So one of the impacts of that, though, and this kind of gets to where there's real opportunity, are the effective fringing fields as a component of that. So now I'm just looking, remember that imaginary block of material that I did that derivation on for what the maximum, FC0, the maximum figure of merit was going to be. That assumed a very simple, parallel plate capacitor. But if I actually look at a real device, a real transistor, and I take its dimensions and how thick, my source drain contact regions are, like how deep that might go, and what my drain source resistance is, et cetera. And I actually go and figure out, okay, well, what kind of capacitance would I get for that kind of, if that was just and using that symbol capacitive type model for that that distance. And I'm going to get about 10 to 80 femtofarads per millimeter. But if I look at the literature, and that's what's shown here on the right, of what people report for FET RF switch, capacitance, that normally you actually see around 0.2 puffs per millimeter, so 200 femtofarads per millimeter, which is to say roughly 3 times what that is. And the reason why that's different, that I would argue, is that it is a function of the fringing fields, because of course, a parallel plate capacitor is actually a relatively poor assumption for the size scale that we're talking about here. And many of the electric fields that are going to be important to how an RF switch is going to operate are actually passing above the device between my drain and source metallization, and beneath the device through my substrate. Oh, sorry. So, yeah. Okay. So the question was, in what direction is the millimeter? So the RF convention for, when we're talking about designs, whether it's on resistance or off capacitance, that's all referenced to gate periphery. So that dimension is how, which of course is the one direction I don't show here. It would be going in and out of the board, essentially, in and out of the screen. Yes. Yeah, the W of the transistor. All right, so actually calculating fringing fields is rather difficult. You can try to do that in HFSS. You can try to do some modeling in Silvaco, for example, on off capacitances. And it's actually relatively difficult to get converging solutions to some of those. But just from a global, like, well, what kind of ballpark numbers are we talking about? There is actually some interesting literature from, this first published in the 1920s, calculating these kinds of fringing fields for some of the very early work with refrigerators. If you use some of their like, for example, this Palmer formula, and scale it down to the size of the transistors, in which you see that these fringe fields, it comes out to a factor of 3, which is ballpark, makes sense in terms of what the experimentally what you see in terms of what people are actually reporting. And really, most of that fringing is going to be dominated by what's going through the substrate for most materials, because, for example, with gallium arsenide, you have a dielectric constant that's almost 10, versus then what's going through the air, where you have your dielectric constant of about 1. All right, so there is this fringing field aspect that we want to take advantage of. And now I'm going to explain why that really gives us an opportunity to make a better RF switch by exploiting that particular relationship. So getting back to, what is our goal? We want to make a FET that looks a lot like a MEMS device. Well, if I look at a MEMS device, right, well, that's metal. Why is metal so, low resistance? Sorry to be so pedantic about it, but essentially, it comes down to that you have this great carrier density. But if I look at a FET device, FET devices generally, whether it's a CMOS device or a HEMT, operate on creating a two-dimensional sheet charge of electrons. And if I zoomed in just at that sheet charge of electrons very locally, right, on that atomic scale, I'm going to find that high carrier density gives me an effective resistivity very similar to that of a metal, because we're just talking a few nanometers thickness for that two-dimensional electron gas. And then, of course, likewise, in the off state with the metal MEMS, I just separate those pieces of metal. Well, in a semiconductor, if I deplete out those carriers, I get the same effect. So if I can mimic that kind of a metal, right, by instead of having one 2DEG, if I add a whole bunch. So let's say I grow a super-lattice. Each of the super-lattice, so a super-lattice is a periodic repeating layer of a heterostructure. So for example, in gallium nitride, we use an AlGaN-GaN heterostructure in order to support a sheet of electrons between those two layers. And if I stack those, periodically, so I go AlGaN-GaN, AlGaN-GaN, AlGaN-GaN over and over again, I can stack up one two-dimensional electron gas on top of another. And in that way, suddenly I have a way now to dramatically lower my sheet resistance. So, because I'm really exploiting my effective resistivity by just kind of repeating it over and over again. Then I just have a problem of how do I deplete all those carriers? And as I'll explain to you shortly, that's the second part that I need, which is the castellations. So I need a three-dimensional gate, and that allows me to access the charge on the sidewalls. And so I'm pinching from the sides, not from the top. So in a normal device, I am applying my electric field orthogonal to my sheet charge. But in this device, I want to control these from the edges. And that allows my electric field to penetrate and pinch all those off. Yes? So he is a question of whether we do an RF analysis and in particular skin depth. So in this case, so we really haven't looked at what the skin depth limit is. Of course, I don't show any dimensions on here at all, but these castellations are on the nanometer scale. So it's in terms of like where we would be limited by skin depth, that would be a relatively high frequency that hasn't been. I think we'd have to go certainly in the tens of terahertz range before that would be. But I mean that would certainly be a potential limit at some point. Yes.
And they would essentially obviate the need to worry about it because they all spin.
That's right. That's right. And it turns into a very kind of interesting buried channel device because you have, I mean, it's a strange mix of this surface device, but then with a high carrier density, you know, inside of it.
What part of dielectric are you?
So he asks, what type of dielectric do we use between the gate and the material? And so we personally, so we're working in an alloy GaN system. So for us, we find that a silicon nitride is most effective. That's not the only one that could be used and applied. And a lot of the same rules, I mean, that as an aside is, so using a MISFET type of structure is important for this because we do need to make sure that we don't have any conduction between the gate and those channels. So normally with any kind of these HEMT structures, you have essentially a barrier between where your electron conduction is and the gate. In this structure, we're etching those sidewalls, and that gate is then right on top of there potentially, which would then give a leakage path there if we didn't have an insulating material. I'm sorry, say again? Well, so I'm just going to combine myself to switches at this point, but one of the primary qualities that we want for a switch is that it's low loss, which means that we don't actually have any dissipated heat within the device if we're making it properly. So even at really high powers, several watts, we're talking and I'll show you the data a little bit. We're talking just a few tenths of a dB of loss, which then translates to maybe 100 milliwatts of dissipated power, even for a very 36 dBm kind of signal. So the net temperature rise is very modest in the device. So I mean, you're absolutely right that the Super-Lattice does provide a challenge in that those are now barriers to heat conduction out of the device. But that said, though, in terms of device, certainly from a switch perspective, that is not that's really not an issue. Yeah.
Do you have to worry about diffraction do you have to worry about diffraction?
So he's asked if I have to worry about diffraction. Yeah. Yeah. So that's not something that we've come across as an issue today. But
probably, but I mean, if you go to really high frequency, you do more.
The separation.
Right. Yeah. Obviously.
Yeah.
So I'm not very familiar with it, but I was just wondering how if the gate structure, 3D gate structure,
yes.
is similar to FinFET.
Yeah, so I'm going to get to that in just a moment. Yeah, so I have a deeper explanation of that, but yes, that's a good question. So going back to my original derivation, now I'm going to translate that in terms of a HEMT. And so once again, fundamentally, my cutoff frequency is a function of what kind of sheet charge density I can get, what kind of mobility, what is my dielectric constant, as well as the impact of these fringing fields. I will also say that that K factor is also kind of like a fudge factor in that what you'll see, and you might have noticed, is that CMOS is doing remarkably well, silicon is remarkably well relative to gallium arsenide. So if I just looked at my material constants, we think that, well, how is silicon doing so well despite its lower mobility, all that stuff still hanging in there? And the reason, I think, is actually quite simple in that it goes to that fringing field and that dielectric constant, which is to say that if you look at high performance silicon-based switches, they're all SY devices, and so there it's because you're trading your dielectric constant for an oxide, so a 3.9 relative to something just under 10 for a gallium arsenide switch. And so so even though the carrier density and the mobility is not as good, once again, it's these fringing fields. It's much better working on those to have less capacitance associated with it. But so if I adding this Super-Lattice here, that gives me a way now to a lever for this FC0 independent of these fringing fields, so I can add in this extra factor here. How many super-lattice channels can I stick in there? And of course, not quite as good as just bits. If I can put 6, I make it 6 times better, because I still I am going to have to take out some of my area in order to put in this 3-dimensional channel. I'm also need to worry about further scattering effects as I keep on going. But it does give me a really nice way to effectively scale and improve my FC0. So I mentioned that it's based on a super-lattice. I reference up here a really good paper by Heifman in 2003, and this is the paper that I came across back in 2006, which is what really turned the light on for me in terms of I always had the idea in terms of this is what I want to do, but I didn't know how to make it. And when I saw this particular paper was on super-lattices for optoelectronic devices, not RF devices, certainly not RF switches, but that idea of like how to grow those super-lattices in Algan was very instrumental. And this plot on the bottom shows, as a function of channels, what are measured sheet resistance for different channels. And that's kind of showing you how that is effectively scaling as 1 over n. That's not quite 1 over n, as I mentioned, because there is some scattering mechanisms that you have to account for as you go to more and more channels. But you can dramatically reduce your on resistance. All right, so finally, so with the super-lattice, that gives us this lever to reduce that on resistance that we have between the source and the drain. But of course, because, as I mentioned, I care about these fringing fields. Well, when I'm doing a super-lattice, my super-lattice is really on a nanometer scale in terms of my total thickness, whereas the dimensionality of my fringing fields, that's on that micron scale. And what that means is that whether I have 1 super-lattice, 6 super-lattices, 10 super-lattices, to first order, my off capacitance is the same. It's not impacted whatsoever by that. And that's what I'm showing here on the plot on the right. So on the left plot, I'm showing again that plot of off capacitance for various technologies. On the plot on the right, I show when I have, starting off with, here's my off capacitance that's measured for just my conventional GaN device. So no super-lattice, no etched paths. Now when I etch and I add super-lattices, I'm getting the same kind of off capacitance. But of course, my on resistance is changing dramatically as I put in my super-lattice. So, and I need to have that etching with those that 3-dimensional gate, because if all I did was a super-lattice, the device would never work. So people started working with super-lattices on FETs back in the 80s. The problem is that they don't really turn off. And the reason, so this is a Silvaco simulation up there on the right. The green shows electron density, and what that's showing is that it's depleting out as you increase the gate bias. But I can't deplete out all these channels of electrons without exceeding the critical field strength of my underlying material. My device fails and the smoke comes out. And so that's why I go to this 3-dimensional structure. And it's different from the SlickFET. The SlickFET is distinct from that FinFET structure. So on the left, of course, I show the SlickFET structure. A FinFET is notable. Of course, that's very common in the silicon world, certainly the deep node devices. And that's kind of like a conventional device that's been kind of corrugated, because it's still very much of a surface channel device. It's still very where you're applying your field orthogonally to this device. So it does have some similarities in terms of it as being a 3-dimensional gate. But what makes the SlickFET distinct is having that 3-dimensional gate, but then also applying the fields from those edges. And the name of the device, this Castellated, so this actually dates back to my first boss at Northrop Grumman, Chris Clark, who had developed back in the 80s some what he called a Castellated device, which is making this kind of a 3-dimensional gate. It's much more like a FinFET, actually, a FinFET structure for our purposes. And so we just kind of adopted that as a name, and also because when I was trying to come up with a name, it took me a couple of years to come up with the SlickFET name. It worked out well to make the SLC for the Slick. Absolutely, that's right. That's the critical. So yes, the turn-off ability is a strong function of the dimensions, and this the SEM micrograph kind of illustrates that. So you can see this is a close-up view of a SlickFET between the source gate and the drain, and you can see that the dimensions of these constellations. We're talking it's at the sub-micron scale for all of these, and it's critical that those are the right size and proportion relative to your charge density.
We have a bunch of them in parallel.
That's correct. A bunch of those in parallel. All at the same time.
So is that a challenge?
Nope. It looks from a device standpoint, it looks like a conventional device as far as that goes. And so, but it does give us this way to reduce that on resistance without impacting the off capacitance, and that's really the secret to making a better RF switch. So in terms of device characteristics here, on the left I show an IV curve showing both a 10-channel and a 6-channel version. And for those of you who aren't terribly familiar, like the 2 amps per millimeter that we're getting for a 6-channel device, that compares to 1 amp per millimeter for a conventional GaN device, if I just made a conventional GaN device. And then the 10-channel I get better than 3 amps per millimeter. In the IDS versus VGS, you can see that we're getting better than 6 orders of magnitude of on-off ratio. And the G sub M is kind of an interesting shape, and that just reflects that, once again, that sidewall pinching. So it's a little bit different looking than a conventional GaN device because it's a little flatter than you would normally see. I believe that these are all 1.6 microns, source drain spacing. And then quarter micron gate. So going back to that plot I had where I showed FC0 as a function of time, and now I'm going to superimpose what we've measured in the SlickFET the last 6 or 7 years. And I'm a firm believer that the best data cannot be contained by any graph. And so as you can see that we've achieved, we're well over 3.1 terahertz. If you actually go by it, like our hero devices were like 3.6 terahertz in terms of what we've been able to demonstrate. And this mainly shows that this is in fact a way to effectively scale switch performance that really hasn't existed before. So, and if I return to that single pole double throw switch comparison that I brought up earlier, at the top now I've superimposed upon this some results of our single pole double throw switches, broadband, DC to 20 gigahertz, for both the 6-channel and 10-channel SlickFET that you can see here. And across the band, we're getting great isolation, 30 dB across the band, but now we're achieving quarter dB or better of loss across that, which is to say that as good or better than the MEMS can achieve. So okay, right here. Yeah, these are the two SlickFET. So this is 10-channel, that's 6-channel. So better insertion loss performance than you can achieve with MEMS, but in a FET. So that means that you've got the reliability, you've got the speed. I won't spend too much time on this. This is an illustration of what does FC0 means. On the plot on the right, I show kind of a comparison of FC0 versus what other people have reported their technologies to be at. The plot on the left is looking at a simple model of an SPDT switch of what kind of FC0 would you need to hit a certain performance. So this is for a broadband DC to 50 gigahertz. And it's essentially showing that you need to have better than a 1 terahertz device if you want to have low loss, really broadband. So this is getting to that the current, like just on doing the same things the same way with FETs, that's never going to get you to a low loss broadband switch. You have to get a much higher FC0 to achieve that. And if I look at different frequency ranges, so the plot on the left now is plotting DC to 6 to 12 to 20, and looking to see where they roll off essentially as a function of FC0. And what this is kind of, once again indicating, I want to have a low loss device. If I want to do very broadband, I need to have a very highly capable high FC0 device. So I'm trying to do narrow band. This gets to that insertion loss isolation frequency product I was describing to you earlier, I can get away with a much lower FC0 as long as I want to do narrowband. So I care about my insertion loss, I care about my isolation, I also care about my power handling. For an RF switch, my power handling in the on state is a function of what my current is. So I'm operating here in the linear region, and then at some point now I'm going to transition from my linear region to my saturated region. That's where I'm going to start seeing, higher insertion loss, that my resistance of my switch is going to look larger because I'm going to move over here to this saturation region. And similarly, when I'm looking at my off state, there I'm worried about inadvertently turning my device on, that my input power is going to essentially float up my device and self-bias it in the on state. And so it's off, it's great, but at some point then, based on what the threshold voltage is and what gate bias, it's going to turn on. So I can use a higher gate bias, a more negative gate bias, to turn it off harder, and I can get more power and more power. But at some point, of course, then I'm also limited once again by what's my ultimate breakdown of the device. And so that's where there's this natural optimum in terms of my off state voltage. So here, so what I care about for high power, I want really high current density, I want high breakdown voltage. That's really what it boils down to. And then for linearity, what I'm going to care about, once again, for my switch, I'm swinging back and forth on this linear region of the curve. And so I want to have a very high IDSS, because where I kick over into the saturation region, that kind of limits how much performance I can get, how much I can be backed off from it. So once again, so power is very close related to, in a switch, its power handling capabilities is closely related to what kind of linearity performance I can get. And I can trade a little bit in terms of what my design is, depending on my frequency, where I can make a bigger device, for example, at lower frequencies, which is going to allow more power and more linearity. But as I go to higher and higher frequencies, then I'm restricted by, I need to shrink it down so that I have a lower capacitance, and that's going to restrict my power handling and my linearity performance. So there I just need to have a better FC0 essentially. So the SlickFET, of course, comes out really well in the power handling and the linearity regime, and that's because, so we're using a wide bandgap semiconductor, we use an AlGaN device, and that has, as I showed you before, twice the current of a conventional GaN device, which then translates to 4 times the power handling as a switch. This shows some devices where we got essentially what we would predict for that kind of power handling. So the one on the left, for a relatively modestly sized device, this is 4x100, and it's passing 16 watts without having any kind of signal compression. Down here on the shunt device, this is showing that walkout where I have to keep on increasing my gate bias to increase what my power handling is on the device. And then in terms of my linearity performance, what we've measured is in excess of 60 dBm of linearity around at 10 gigahertz with 2 different tones of spacing. It's also a very fast switch because just like all switches, there's not a lot of capacitance that I have to worry about. What actually slows down the switch mostly is that for all these RF switch designs, I have to make sure that I don't have RF signal leaking out of my gate. And so I have to put a relatively large, usually 10 kilo ohm resistor in series with the gate to essentially make a filter through the gate so my high frequency signals don't leak through it. But even so, we're looking at rise fall times of in the 10 to 20 nanoseconds, and then settling times of in the 100 nanosecond range. So going back, all the way to the beginning, what do we want to have in terms of performance for my device? So I want to have low loss and low on resistance and low off capacitance. The SlickFET gives us an FC0, which is 3 to 8 times better than anything that's been reported in other technologies. We also want to have high current density to give us power and linearity, and the SlickFET offers, the GaN SlickFET anyway, offers 2 to 3 times more current, which is 4 to 9 times more power handling. And we want to have high blocking voltage. And being a gallium nitride-based system, it has a very high blocking voltage. We don't want to dissipate any power. And once again, the SlickFET, with that, we're looking at the MISFET structure, which means that it requires nanoamps of current, so very minimal power dissipation. It offers nanosecond switching speed, and then being a FET and a MMIC has all the wonderful things of its reliability, its our ability to integrate it as part of a larger MMIC process. So in summary, RF switches are critically important to RF system performance, and particularly wideband system performance. But historically, our ability to achieve system performance in wideband systems has been limited because of the limitations of those component technologies, particularly with MEMS and pin diodes. The SlickFET and that as a device concept provides a way to scale switch performance similarly to the way that device scaling has improved amplifier performance and has dramatically improved the state of the possible for a lot of different RF architectures, including, as an example, providing for the first time these low-loss solid-state switches that offer just a few tenths of dB of loss across a wideband with very high isolation, all while at the same time offering high power and high linearity. Thank you for your time.
Can we go online?
Sure.
So, stuff.
Well, yeah, that's the other problem.
Thanks.
Can you guys repeat that question?
Survey
Sir,
stuff.
one.
For now, let's say. Well, we're getting ready to change our. I need to find out if they actually answered that question. Getting ready to change our timekeeping system. We're no longer going to be using SAP.
Well, I was given, actually, I
You got
logged in
that question online?
one of those sessions. Got through about 10 minutes of it. Okay, there's going to be a training.
All right.
Well, there's other stuff that affects employees more so than you. But yeah, there will be a time training session, which is the part I was figuring would include you as part of it.
Yeah.
As of this time, there's really nothing you can do other than count that.
That's a long way out.
Well, the implementation for it, yeah. But you're gonna have to
Yeah, so the question was, are most of the power losses conduction losses, or I assume you mean like switching losses? Yeah. Yeah, so for RF systems, unlike power switches, it's mostly conduction losses. That's just because the relatively, like one is, in terms of the size of the devices that we're talking about, the switches, they're not that large. And so the amount of charge that you're pushing in and pushing out of the device in order to turn it off and turn it on isn't that great relative to, of course, how much power I'm flowing through it, and so that's where I really see the power dissipation associated with it. It is CW, that's right, and the RF signals generally are CW. They don't necessarily have to be actually, but it does get to like in terms of the switching speed varies widely depending on your RF system. So some RF systems, like Castellated systems, require nanosecond switching, which is say really like 20 nanoseconds or 50 nanosecond switching. That's on the high extreme end of the switching. Other ones might be, they might just switch more like on the second, hour, day kind of time scale, like a really slow switching. So it might just be on. I mean, so it really is system and application specific. I'd say millisecond is probably the most common of those, but in all cases, relatively slow switching in terms of the frequency of the switching. But in all cases, the switches, so for example, like that SPDT, which is the SPDT that I showed in those results, that can conduct around 6 watts of power, but the switch periphery itself is only 600 microns total W. So so it's 600 microns, and then it's an L of 0.25, quarter micron. So in terms of that total area, you're looking at just 150 square microns of material. So it's, you go ahead and do the math, and it's a very small capacitance associated with the switching energy for it. So 6 watts is, remember, so 6 watts is passing through the device, right? But you're not switching that. That's not the energy that you're switching back and forth. That's the RF energy going through. The amount of energy, the charge that you're doing with an RF device, right, is just the charge in the channel that you're pushing back and forth, which isn't 6 watts. That's very, very tiny. The 6 watts is just that CW. I'm allowing 6 watts to as a gatekeeper, kind of like through or not through. So in that sense, it's a little different from like the power switch world in terms of and the dynamics associated with it. Right, absolutely, yeah. That's, I mean, and I used to. Sorry. He said he's used to the switching losses being larger than the conductance losses. And what I did early on in my career, one of the projects I was involved in the power switch technology programs we had at Northrop Grumman, including our DMOSFET and some of our SIT work that we did, doing the very high voltage 10 kilovolts type switches. And that's exactly that kind of trade where you're worried about that switching losses, but those devices are a lot different. I mean, so where we have these really large area devices, in terms of like their footprint, they're enormous, relative, or they can be enormous, relatively speaking, versus these devices. If you're not looking under the microscope, you can't see the devices, even though you're putting watts of energy through them, because once again, it's better to think of it as that these are really interrupting transmission lines, right? Like that's how much power I'm putting through my transmission line, and I'm just, putting a block or releasing, going through this transmission line. But it's not the same kind of thing that you have in where you're doing like a DC conversion switch to like an H-bridge or something like that.
Okay, we have a question here in Lexicon.
Well, it potentially could be, although I'm a little skeptical that oh, sorry, I keep on forgetting to repeat the question. So he asked, what kind of system is this going to be in? It won't be your cell phone. And my response to that is that it potentially could be, although I am a little skeptical that there's a reason why the commercial world hasn't ever done this. So I'm not quite confident enough in my ability, or arrogant enough in my difference, in that why was I able to come up with this and the rest of the industry just never did it? And I would say the reason is because the rest of the industry never had to. It was never a problem. Going back to that issue of what I mentioned, of that loss, isolation, frequency, bandwidth. So commercial systems are, what I would say from a Northrop Grumman viewpoint, are notoriously narrowband. Even what they consider to be wideband are outrageously narrowband. And when you're working in those kind of systems, there's an enormous opportunity to resonate out the capacitances right. And so you can get away with a lot without that. But as soon as you go to a wideband, there's no way to do that. I don't know that the commercial world is ever going to need that kind of wideband performance. Now, for our systems, for Northrop Grumman systems, this is absolutely critical, because this really gives us all kinds of capabilities that we haven't had. For all across, yeah, every RF system, so radar and EW and SIGINT and comms, all these different systems. Yes.
I think there's a question online now.
Yes.
Yeah. Yes, this is Vivian up in Lincoln. We have a question in our room.
Go ahead.
How you doing? My name is Eric Sebron. So my question is, is what's next? Is that it? Like, can we continue to improve the SlickFET? Is there much room for improvement? Is there other
Absolutely.
technologies that have advantages?
Yeah. Okay. So the question is, what's next for the SlickFET? Are there opportunities to continue its improvement? Is it done? And of course, you know, that's one of my favorite topics of that. No, there's enormous opportunity to continue to advance that technology, that we've just really scratched the surface of this particular topology and what it can do. So right now we are working on transitioning our baseline process into a manufacturing process so that we can have it more widely deployed, and in particular, you know, get it into you know, our various systems. And so that's, you know, increases TRL to TRL6, increases MRL to MRL6. But even just as a switch itself, as a technology, there are a number of different improvements that are worth pursuing to further improve our performance. We haven't hit the ceiling of what that performance is. As we go to higher frequencies, you know, higher performance is always going to buy you something. And there's a number of things, you know, so one of the things that we've just recently we won a part of the DARPA MTO program, the DREAM program in TA1, and we were going to be developing a very high power density amplifier with this technology and eventually, of course, marry it with a switch and have a full MMIC process of amplifiers as well as the switches. So in terms of the vision, you know, there's still quite a bit more work to be done, further improving certain aspects of the switch, but also bringing on new capabilities and probably most importantly, getting what we have right now into a production mode so that our systems can use it.
Thank you. Questions online?
No more at Linthicum.
Very cool.
Thank you.
So I actually had a question.
Yeah.
What angles are your sidewalls?
Yeah, that's actually a very critical aspect. Sorry, boy, I always forget that. So the question is, what angles are the sidewalls of the gate? That is a real critical aspect of the design of the internal design of the device. I won't say the precise number because that is part of our IP associated with the device and how to make it, but it is extremely steep, much more so than you would normally see in the kind of fibs that people generally share.
And then I guess a follow-up question would be, I would think during your fabrication process that your sidewalls would be maybe have dangling bonds. Does that also play a role? In
Absolutely. So the question was about the dangling bonds, and that's another really excellent observation. So how we form the SlickFET castellations is through a dry edge process. That is relatively speaking, a violent process. It does leave all kinds of surface states, and so a big part of the process is then dealing with those surface states to mitigate and eliminate them so that they don't end up affecting our device functionality.
I could imagine like when the device is off, it doesn't matter, but when it's on.
Right. Yeah. So I mean all those. So the question is, or the comment is, you know, I imagine that when the device is off, it doesn't matter, but when it's on, it does. And that's also correct. That those surface states really impact things like the dispersion that you see on the device, the switching speed that you see on the device. All those things matter. And so to achieve really high quality switch performance that you would want, you know, the kind of switch that our system folks would be, you know, wanting to introduce into their systems, you do need to have a process that deals with those interface states appropriately.
Follow up on although your vacuum goes to nitride, you cannot avoid oxidizing lateral oxidation to rubber nitride.
So, yeah. So the question is, what about incidental oxidation of like the allogan layers or the gallium nitride layers? I will say that. Well, I had mentioned before in the talk that the device is a quasi-buried channel device, and that's actually true. That so in your normal device, all your carriers are just a few nanometers away from that interface. In this device, that's actually not the case. Most of the carriers are actually tens of nanometers away from any of those interfaces, those surface interfaces. So that does lessen that impact. That said, in terms of those surface states, things like that, oxygen contamination is something that you really do have to be aware of. Make sure that is taken care of. And so, surface preparation of your films and during the processing, how you're handling your wafers during the processing and those sequences, those are all very critical in terms of to achieve the results that you want at the end of the day.
Kevin was saying that it didn't think it was far off would make a difference. So that I'm somewhat asking more about that because I just think every state may give places for a channel.
Yeah.
Of leakage current, but apparently not.
So the question is whether or not how RF matters, whether the surface conductions. The issue really comes to if you have traps and then you're having to fill and empty out traps back and forth. That's the kind of cycling that really hurts you, because you can develop these virtual gates in the device, and those virtual gates can kill your device in the sense that your device doesn't want to turn on, essentially. Like, it doesn't respond properly to, that's right. Nice to meet you. But the off-state resistance is very important. You need to make sure that, I mean, for the device to work properly as an RF device, you really do need to have, very similar to a power device, you need to have at least 6 orders of magnitude between, what that off-state current is. If that off-state current starts creeping up, between the source and the drain, your RF performance also goes to the tank.
How do you deal with that?
I gotta go, but it was a great talk.
Oh, thank you. Yeah. Okay, great.
How do you be careful? How do you make sure that there's no leakage?
Yeah, so the question is, so how do you make sure that you're careful and there's no leakage? And so that's where we're starting to get into like the actual process techniques and I won't say tricks once again. But to a certain extent, I mean, number one thing is experience on having made all the mistakes and the wrong things initially, so that finally you are left no choice but to do the right thing. So from that sense, it's like all process integration.
Oh, really? They bought it? I thought that we bought it.
So with our current baseline, the question is, what is our maximum off-state voltage, maximum on-state current? The device as we've built it right now has a breakdown voltage. Our baseline architecture has a breakdown voltage of 40 volts. From an RF perspective, that's pretty decent. We are looking at geometries and devices, architectures where we can increase that breakdown voltage to 120 volts or so. I've also had ideas, since I used to do the power device world, of translating the structure into more of a power device where we can increase that to 600 volts, 1200 volts to be more similar to the kind of regimes. But there's not an enormous amount of interest at Northrop Grumman in some of those. We'll see if I'm ever successful in getting any of those architectures off the ground. From a current density standpoint, our current density is 2 amps per millimeter, which means then, and so in terms of how much periphery do you use, that's really going to depend on really the capacitance that you can tolerate for the frequency that you're asking about. Kind of fixes that. So for example, that SVDT that I was showing you, that so it's designed to work out to 20 gigahertz. That has that the series device on that is I think 225 microns, which means that do some public math, that's around a half an amp essentially is what that particular device is. But it's really, obviously you can make it bigger, but if you make it bigger, then you start playing with what kind of frequency regime can this operate in. But essentially, 2 amps per millimeter is the scaled number of how much current for our 6-channel. For the 10-channel, that's 3 amps per millimeter. And actually, normally when we bias these devices, we go between 0 volts for off and -14 for off. 0 volts for on, -14 for off. You can goose that current if you're willing to use a positive voltage on the gate. So if you go up to 1 volt on the gate, that'll buy you, instead of 2 amps per millimeter, you're looking at like 2.3, 2.4 amps per millimeter, or instead of 3 amps per millimeter, you're looking more like 3.5 amps per millimeter. So that can actually be a significant amount of extra power. But generally, though, we are off-state power limited for these RF switches, not on-state power limited. It's an enhanced on, that's right. Well, one of the interesting things about this is that, so I showed you this nice structure, right, of, I beg your indulgence for a second. We have the picture of the SlickFET on the left, and as I mentioned, that it's a MISFET structure where we have these essentially buried channels of the current to connection thing. But there's also a parasitic MOS device here, which I don't show at all, because we have our gate, we have our the insulator and that sidewall. So actually, if you forward bias this device, what you end up doing is that you actually create carriers, an MOS carrier conduction path along those sidewalls. It doesn't really dramatically change the on resistance. The on resistance gets a little bit better, not enough for us to really do that as an ordinary kind of thing. But from a power handling thing, you're putting more charge in it, so you can get more current, and that you really do see that. And that's why, if I look at, I have a plot here. Let's see, where do I have that plot? Right here. Okay, so on the plot here on the left, I actually show. So this is a 6-channel device, but here I'm showing it in 1 volt steps. So I'm actually showing when I have the gate. The top 2 blue curves are when I have 1 volt on the gate, 2 volts on the gate, and so you can see this additional current that I'm getting. So I'll note that you don't see any difference right here in the linear region in terms of what I'm getting at what my on resistance is. That's not really changing. But when I do that, I'm putting more charge in my device, which is increasing what my IDSS, right, it's a function of what my saturated velocity is and my charge density. So I'm increasing that charge density, which is giving me a higher current capacity in the device, which then will translate to a higher power level. No, because it's an insulating gate. So GaN, yeah. So exponential GaN, if I just go on the market and buy GaN amps, absolutely. But that's because they're a MESFET structure. They don't have an insulator on these. So that's one of the many. So I'm using the same material. I'm using that gallium nitride thing. But in terms of what is the underlying structure, like how we make, what goes into that super-lattice, that's actually quite a bit different than any of those than a conventional device. So the conventional GaN device, I have a single heterostructure, and I'm using a MESFET essentially, so I have a Schottky gate on top of that. And you're absolutely right. If I forward bias that sucker, I'm just going to turn that Schottky diode right on. I'm going to see a lot of gate current. Now, some people make MOS GaN devices. Of course, they're not really all that great because you just don't get the same kind of charge density. The SlickFET is a unique hybrid of all of these things, where it has, relies on this super-lattice, so it has that same kind of thing of, I have this super high density hemmed, structure all over it, but I'm, at the same time, I have to worry about, sorry, Oh, it's this way. I'm forgetting which way I need to go in my charts. I have to worry about, that I don't have that contact. So in a regular device, I would, have my gate just up here. I have this material right here, the allogan, essentially forms a barrier between, my Schottky device and this. So at least if forward bias, I'm going to get current, but if I don't forward bias it, I'm not going to get current, so that's okay. In our device, we're using the gate here on these sidewalls. This guy doesn't do anything because of the shielding effect, right? So, all my action is from these edges. If I just made a Schottky, right, a Schottky gate right there, this wouldn't work because, unfortunately, of course, I have these things. I'm showing that there's some depletion here, but essentially, I'm making this almost or practically a direct connection between this gate and that connection. So I need to put an insulator between here, right, around all this thing. So at the same time, I'm using this an insulating gate, and that makes this kind of a version of a almost like it's a misfit, but it also gives me this opportunity to that I could potentially exploit of creating a inversion layer on here, when I go to forward bias, and so. But I don't get any gate leakage through there because, and so it's nanoamps of gate current during all operations. I mean, the only time that the maximum time that you see gate current in ours is when you go high negative bias, just because you're at negative 14 volts or whatever. But in all cases, though, we're talking nanoamps per millimeter, so it's very, very tiny.
I hate to cut this off, but I'm just teaching.
Well, let's thank our speaker again.
Really good session.
Oh, thank you.
Down. So that was a really good session. We never had such interaction with the folks online. So.
Yeah, well, here's what, if you don't mute them, it ends up on the recording. So you almost have to mute them. Yeah.
It's just, they were concerned about that. Comment things like, understand the key. If you're muted, that interaction with the speaker, you're losing all that during the thing.
Yeah,
but your point. Gee.
Or maybe you should leverage the chat more. So they can ask that question. If I see that pop up, I can then relay it. Yeah. All right.